So today's topic is again on a theorem about P of x, where x is compact metric space. In the last class, we discussed about compact subsets of C of x, how to determine that, and the necessary and sufficient condition for a subset to be compact. Today, we want to discuss something about A is an algebra. I will define what an algebra is. I will tell you what an algebra is. You must be knowing also. If you have a subalgebra of C of S, where x is compact and its continuous functions on x, when is this dense? Okay, that is the question we are going to discuss, and that is answered by so-called Stone-Weistrass theorem. A particular case of it you might have seen earlier, which is called Weistrass theorem. Polynomials are dense in continuous functions on 0 any interval or so. So this is what we want to discuss, Stone-Weistrass theorem, which says the following. So I will write the theorem again. Here it is just a discussion. If we have so what is a subalgebra? Let me make the definition first. You have C of x. So an algebra is something which is a vector space as well as a ring. Okay, C of x is a vector space. We have seen it's a norm. It has a norm. It's a norm linear vector space, and so you can add, you can scalar multiply, and you can also multiply through functions, point-wise multiplication. If you have f and g, then you can talk about f times g. Okay, so it forms a ring. You can see that it's a ring. It's associative and all that. And the multiplication and the addition, scalar multiplication are compatible. You can take, there is a distributive law. You can take the scalar inside and all that. You know all those definitions. But we don't need algebra. We know this is an algebra. For us, algebra is the following. A contained in C of x. This is enough for us. Subalgebra. If A is a subspace, a vector subspace. A is a subalgebra. If f and g are in A, then f times g, the point-wise multiplication, gives you another continuous function, and that is also in A. That's all. Then the theorem, the Stone-Weistrass theorem, is the following. This is what we are going to prove today. That is A contained in C of x, a subalgebra. You have a subalgebra which contains scalar, containing scalar means constant functions. Okay. The function f of x equal to some fixed number r. So there are two cases. So we have to assume that it's a real vector space. Okay. CXR, real valued, continuous real valued function on x. If I put C, it is continuous complex valued function. So this theorem is for real valued function. From this, we will derive the theorem for complex valued function. Okay, so this is a subalgebra containing constant functions. So f of x equal to f of t equal to some constant for all t. This is constant function. This contains a constant function and separates points. We have already defined this. What is separate points? Separates points. What is separate point mean? That is, if we have x, y in x and x not equal to y, then there exists a f in A such that f of x is not equal to f of x. Okay. You have a single function which takes different values and x and y. For any x and y, xy in x, xy in capital X in the compact metric space, you can find a function which differs on those 2 points. Okay, this is what separates point. We have already seen that on any metric space, continuous function separates the points. We already proved it. F belongs to that A. A separates points. The definition is A is separating point. Okay, maybe I should write it as a separate definition because I've already, this is about A. We say a subalgebra A separates points if it satisfies this condition. We have already defined this. Okay. So if for all xy, there exists a function f in A. We already know that C separates points. Given any 2 points, there is a continuous function which differs, which we prove for any metric space. Okay. Now we are saying that some A, this is just a subalgebra, need not be closed or something. Okay. The subalgebra which contains constant and separates points, then it should be its dense there. That is the question. Then A closure equal to C X R. Okay. The R is, this is for real valued one. There's a similar statement for complex valued one. We will derive from this. We will state it later. So this is the theorem we want to prove. Okay. The idea is the following. So it separates points. That's an important condition. So if separates points means what? So if you have xy in x, x not equal to y, okay, then there exists a f in a such that f of x is not equal to f of y. So you can put this in the denominator, which is not 0, f of x minus f of y. You can write it like that. Okay. And then you can write f of z minus f of y. I can put in scalars alpha minus beta, alpha plus this. Suppose the A contains scalars. So this is the function. This is scalar function, alpha, beta or scalars. Alpha, beta are in real life. They are just real numbers. Alpha, beta are real numbers. Then alpha is a constant. This is a function. Okay. So this is in A and it's an algebra. It's a subspace. We can add two functions. And this is just f of z. F is there. So f of z minus f of y is there. This is just a subtracting a constant. F of y is just a number here. Okay, only z is, this is g of z equal to this. Okay. G of z equal to this function. This is a new function. Okay. Then g of x equal to alpha, right? G of x, g of y equal to alpha, is it? F of z minus, f of y minus f of x. Let's say f of y minus f of x. Now it's okay, just to get alpha and beta correctly. Minus f of, so if you put g of x equal to, here it should be f of x, right? Yeah. G of x is, that becomes 0, so it's alpha. And g of y equal to beta. X and y are fixed here. Z is the variable, okay? This is a new function, which is linearly interpolated. That's all. Okay. So then you have g of, so given any number, alpha and beta, given any point x and y, this g is in A, right? I use these two conditions. A contains constant, A separates point. Using these two conditions, you can get a function g, okay, which takes the value at any point you can have the value alpha, any alpha. At any other point you can have the beta, and g is continuous. Okay, so this looks like you get all the functions, right? This is a hint. But then but this is not, this is only on these 2 points. You want to get any function. But then if you have an f here, some f, around this g, g takes the value except, but around this x, it cannot go too far because it's continuous, right? Given an epsilon, you can't go, so that will be an open set. Okay. And you take this open set, that open set, if you take the x over all of this x should cover x, right? Because x, I will write all the, it's just to give you an idea. Okay. So, and there are only finitely many, because it's compact, there are only finitely many open sets which will cover this. Okay. So you can take the minimum of that, maximum of that. Okay. So this is the idea, basic idea. But as I said, you have to take minimum and maximum. So if you take two functions in A, we want the minimum of those two functions to be again in A or A closure. Okay. Maximum should be again in A closure. But to prove next, we want, as I said, this is the basic idea. But then, as I said, we will consider these kind of functions. Given any f, we will consider these kind of function. Then we will kind of take, around each neighborhood, we will take a minimum over, we are only finitely many open sets. We will take the minimum over that and maximum over that. So we would like to have, if you have any two f and g in this A, then we want to assure that the minimum of those two functions is also again in A, and the maximum is also again in A. Okay, but then minimum and maximum or minimum of two function f and g, this you must have seen in calculus or something, which is just half of f of plus g plus or minus mod f minus, right? Right? One of them will cancel. The maximum, I mean, this is just minimum of g means at each point, this is real valued, okay? To take the minimum of f of t and g of t and the or maximum of f of t, that is a new function. That function is continuous function because modulus is continuous and it can be written like that, okay? And the point is that function is again in the script here, in the algebra. Okay, so that we want to prove. Once we prove that, we will use this idea to get I mean, we will show that it is dense. Okay. So to prove minimum or maximum, you have to prove that the modulus is there. Okay. But then modulus is nothing but square root of f square. If f is a in a, f square is in a because it's an algebra. But then we want the modulus, so square root should be there. Okay. So square root of f square should be there. So for that, we use the original Weierstrass theorem, or I11. We don't need the original the full statement we don't need. We only need the statement that the square root function on any interval can be approximated by polynomials, uniformly by polynomials. We want uniform. Okay. So the square root, so modulus is the closure of A we want. And this is just the idea I am stating. We'll go through the proof completely. Okay. Okay. So we want to prove that the square root function can be approximated by polynomials. Once we prove that, we will get the modulus in this A. Once we have the modulus, minimum and maximum will be there. From using this idea, we will prove that. So that is the plan. So let us start one by one. First statement is we want to prove that any interval is true, but we take the interval 0, 1. That is enough. Or any interval, you can work with that. So on any interval in the real line, we can approximate the square root function. I mean, in the positive real line. Before that, I mean, we will only get point-wise convergence. Before that, I want to prove the following theorem. The proof is very easy. This is called Dini's theorem. That is, X is compact matrix space, of course. And if you have sequence Fn contained in C of X, and F is in C of X, and Fn is monotonically monotonic. That is as a sequence, monotonic sequence, okay? Not as a function. Okay? That is at each point t, f and t is less than or equal to fmt if m is greater than or equal to m, or the other way, monotonically decreasing or increasing. Okay, as a sequence. F is that is, let me write, f and t is monotonic as a sequence. Okay, n in m is as a sequence is monotonic in as a sequence. Okay. Okay. Then F1 converges to F pointwise if and only if F1 converges to F uniformly. I mean, pointwise convergence is enough. If it converges pointwise, then it converges uniformly. So that's the statement. Okay. So if you can prove this for decreasing function, you can prove it for increasing function by taking minus. Okay. And if it is converging to Fn is converging to some f, then you can, I mean, you can shift it, and you can, I mean, you can, I mean, if you can shift it by the limit, and you without loss of generality, we assume to check, okay, F1 decreases to 0. If you prove for decreasing, you can prove for increasing. If Fn is converging to some f, Fn minus f will go to 0, okay, monotonically. Okay. So this is okay. So we assume that Fn decreases to 0. pointwise. F1 t decreases to 0 for all t in x. Now we want to prove that this is uniform convergence. That is, so pointwise convergence means for each t there exists epsilon depending on t, such that after some time it will be less than epsilon. Mod is less than epsilon. Yeah. Ah, that's right. Yeah. I mean, some of them increasing, some of them decreasing. No? You want to ask that whether some of them, some of t will be increasing, some t. Yeah, yeah. Everything is, I mean, that will not be possible, but you assume that. Either monotonically increasing or monotonically decreasing. Okay. So that's why I'm assuming here the effect is. Okay. We will anyway use for a increasing sequence, positive increasing sequence. Okay. That's what we will use it. Okay. Let us define un equal to all those x in x such that fn x mod is less than fm x is less than epsilon for all m greater than or equal to n. This anyway happens for each x. Okay. For each x, there exists a n such that after that n, it used to be smaller than epsilon because pointwise convergence happens. Okay. But then because it is decreasing, this is equal to x in x such that, I mean, there is no need of mod because we assume that it's positive. Okay. So this is equal to f nx is less than epsilon. Right? Because all fmx after that is going to be smaller than this because it's decreasing. Okay, we can assume this. Okay. Since fn decreases to 0 pointwise for all t, union of n equal to 1 to infinity un equal to x, right? Given any x, it's going to be sit in some un because there is a pointwise convergence. Okay. But then since x is compact, there exist finitely many of them. That is I equal to 1 to n u ni equal to x. Okay. I mean, there exists n1 up to some finitely many of them. Okay. Now let n naught equal to maximum of n1 up to n whatever. Okay. Then you notice that this un is also increasing. Un is increasing. Right? If something is less than this, then if m is greater than this, that will also be less than epsilon. Okay? So un naught is equal to union of that I equal to 1 to n uni equal to x. That's what this is. You take the maximum of that. Okay? So this n naught gives the condition. Okay? So this implies f from x is less than epsilon for all x in x if m is greater than or equal to n naught. This is precisely the meaning that fn converges to 0 uniformly. Okay, this is the statement. This n naught should be uniform for all x. Okay? This is the uniform convergence. Okay? That's all. So this theorem is actually it's very easy. I just spelled out all the details. Okay. So this is fine. We want to use this to prove that the square root function can be approximated by polynomials. Okay. So yeah, you assume that is the definition. It's either increasing or decreasing. You assume that. Okay. So next lemma or proposition. f of t equal to square root t on this interval 0, 1. Okay. Then there exist polynomials. Say Pn on 0, 1 converging uniformly to f. F is a square root function. Then we get this is the this follows from Weierstrass theorem. I am not using Weierstrass theorem. I'm just because I only need this statement to prove Stone-Weistrass theorem. So I'm just proving it. Okay, it's direct, so I'm just proving it. Okay. So I take polynomials. I will define Pn later. So I define polynomials. Q0 is identically equal to 0. And Q1 equal to 1 by 2 T plus 0, of course, if you want. I write it 0. And Qn plus 1 equal to half T plus Qn minus 1. Q is this function. I just define Qn plus 1 to be Qn. Inductively define like that. Then first statement is Qnt is greater than or equal to 0. And Qnt is less than or equal to 1, greater than or equal to 0. Second statement, Qn's are increasing. It is 2n plus 1 is greater than or equal to Qnt. Okay. So let us verify this. Then the claim. So we prove it by induction. Okay. No problem. I claim that Qnt is between 0 and 1. Okay. The range. And I claim that Qn, this is increasing. This is increasing. Okay. So the first statement, proof by induction, proof of claim is by induction. So Q0 is of course between 0 and 1. Okay. Now it's clear that Qn, so if you assume Qnt is greater than 0, then Qn plus 1 is greater than 0. It's clear. Okay. And second, if you assume Qnt is between Q0 is less than 1 for all t. If you assume Qnt is less than 1, then Qnt, this is less than 1. Something less than 1, something less than 1 divided by 2 is less than 1. Okay. So I don't want to do the detail by induction. Okay. So just induction. We know Q0 satisfies this. If Qnt satisfies this, Qn plus 1 satisfies. So induction proves it. Okay. Second. So I want to prove that Qn plus 1 minus, sorry, Qnt. Qn plus 1 is greater than Qn. That is the statement. Sorry, I missed the n. Okay. Now I write this Qn plus 1 t minus Qnt equal to half into, those t will cancel. Oh, I'm sorry. There has to be a square here. I missed the square. Please, there should be a square here. T plus Qn square. So that is what I get here. Okay. Q. So I get Qn square. See, here I will get Qn square. Here I will get Qn minus 1 square. Right? If I just write the definition, Qn plus 1 minus Qn. Okay, this is equal to Qn minus Qn minus 1. So Qn plus Qn minus 1. Right? Now, if you assume, so now we know that Q1 minus Q0 is greater than 0. Okay, for n equal to 1, this is true. If you assume for n equal to n, that is Qn minus Qn minus 1 is greater than or equal to 0, then Qn plus 1 minus Qn minus Qn, this is greater than or equal to 0. These are all positive, so this is 0. So again by induction, this is 0. Greater than 0 by induction. Okay. Again, this is true by induction. Okay. So we have got Q0, Qn plus 1, they are increasing and they are bounded between 0 and 1. So for each t, there should be a limit. Okay. So So it's the increasing sequence for each t, and it's bounded. So Bolzano-Weierstrass says that there exists a q of t in 0, 1 such that q and t converges to q of t for all t. This convergence is uniform because this conversion should be uniform because of the earlier Dini's theorem, okay? Because it's increasing. Okay? And the Dini theorem implies Qn converges to Q uniformly. Let's keep it as it is. But then we know that Qn plus 1t is equal to half of T plus Qn square. Yeah, Qn square t. Okay. But this converges to Q of t. This is equal to half into t plus q square. Okay. Now this is a quadratic equation in Q of t for each t. You fix a t. This is a quadratic equation in Q of t, okay, and the t is a coefficient. And you will have two roots, but the other root is not possible. It will become greater than 1. So this implies that Q of t has to be, if you, I mean, let me not write the detail. It will be, we will not get root t. We will get 1 minus square root of 1 minus t, right? Minus b plus or minus plus will increase. I mean, this is 2q of t equal to t plus q square t. Okay, the b is minus 2. Okay, minus b is, I mean, but we will get this coefficient 2 the bottom, so this will become 1. B square minus 4ac. So b square will get, you will give a 4 here, 4ac, that 4 will cancel with this 2. So it is 1 minus t. So q of t is equal to square root of 1 minus t. So qn of 1 minus t, 1 minus this will converge uniformly, will converge to square root of t. Huh? Root t is the solution, you are saying. Oh, where are you saying this? Maybe. How are you saying this? Maybe then it should be true that 1 minus qn minus 1 minus t should be equal to that. Yeah. Okay. Yeah, you may get root t also directly. I'm just getting this answer. If you cleverly slightly change the definition by taking 1 minus t instead of t, you should get root t. Okay. So I have taken this definition, so I am getting this. Doesn't matter. So this will converge to root t. You just want some polynomial. You call this as Pn. But since the convergence, everything is uniform, you can take, so the Pn converges to square root of root t uniform. Because all the convergence is uniform, and if you add plus or something, constant doesn't matter. Okay? This is uniform. So we have proved that polynomials in the interval 0, 1 converge to this. Now let us state the theorem. We assume this theorem and prove one by one. Maybe not. We will say one by one. We will make one by one statement, proposition, so that it will be clear where things are being used. A contained in C of X subalgebra. Okay. Then what am I using? Then let us see. Minimum of f of g, maximum of f of g is in A closure. Let's see. I mean, I'm not sure. Proof. Let us prove and it will be clear. So I take this function. I take. I want to prove that modulus is in the closure. From modulus, I will get the answer. Okay. So let f is in A, square root A. Okay. And I want to get the modulus of any function is in A closure. That's what I want to do. Okay. Then modulus of f. So I take f square. This is just real value. So this is positive. Then I divide it by the infinity norm. so that this becomes less than or equal to 1, between 0 and 1. Now I applied this polynomial Pn, right? This will go to, here also there is a square. This will go to square root of that, which is f mod f by norm f infinity. Or if you want, square root of this, which is equal to mod f by norm f infinity. This is the supremum, this f infinity is a number, which is the supremum of all f of t, mod f of t. Okay? So I take the square of that, f square by this. So this is less than or equal to 1, greater than or equal to 0, less than or equal to 1. This is the Pn is given by this, okay? by this lemma, whatever, this theorem. Okay? I use those Pn, then the Pn of something will go to the square root of whatever is inside. The square root of that is precisely this. And this is just some constant times that. So this implies mod f is in A closure. Now we know that minimum or maximum or minimum Fg is, I have already said, this is equal to half of f plus g plus or minus mod of f minus. Okay. Now you can add and do that. And so that is in the A closure. So this is a general statement. We are not using separate points or constant content. Now I repeat the statement which I made earlier. Okay, I'll state the whole theorem. I repeat it. A contained in C of x, subalgebra, all, f of t equal to lambda for all t. Constant functions are contained in A, okay, and A separates points. Points of x. Okay? A separates points of x. Given any x and y, x not equal to y, there exists a function f in A such that f of x is not equal to f of y. Then A is dense. That is A closure is C of x. Then C. So this is all are for real line. Okay. I'm sorry. I should have mentioned earlier. Everything is for a real line. Sorry. Wherever. Till now, we are assuming that C of x is real. Okay, real value. The range is real. Proof. So first claim is this. This we have already seen. I'm just repeating. Okay. So for any alpha beta real line and any xy in x not equal to y, there exists a f in A, g or f, maybe g in A, such that g of x equal to alpha, g of y equal to beta. Of course, there should be different point. If alpha is not equal to beta, then it's not possible. So, a different point, this is true. And the proof is just simple. Just this, g of z equal to alpha plus alpha minus beta. What is the statement? Beta minus alpha. No, but what comes here? What is f of x? What is f? There is no f here. G of G of x should be alpha. So right. Yeah, I was just wondering what is here. Let f be in A such that f of x not equal to f of y. Yeah, good. Then g of z equal to alpha plus beta minus alpha. Earlier they write alpha minus beta. So then f of z minus f of y or x divided by f of y minus f of x. Let's check. I think this works. This is not equal to 0. Yeah, this works. So this is the function. Okay, this is which is continuous. Now proof of the theorem, rest of the theorem. So for xy in x, okay. So what do you want to do? So to prove the theorem, so let f is in p of x. Then, I mean, this f is different from this f. Maybe I call it h. Okay, f, g. Now h I'm going to use. So, okay, let f. Okay, this is some f naught. I just want to show, I mean, this f is different f. That's what I want to say, okay? F is in C of x. Then we want to approximate by some g up to epsilon. We want to approximate. We want g in A such that mod of f of x minus g of x is less than epsilon for all x, right? That's what you want. Okay. So given a f, I want to get a g. Okay? G or h, let's say h, because g is also used. H, okay? Such that is happens. Or g is also fine. Okay, sorry, g itself. So for x and y in x, okay, choose g subscript xy in A such that g xy at x is equal to f of x. I mean, this is the alpha in that claim. For any alpha, you can get a function which takes the value alpha at x and beta at y. So I take the alpha to be f of x, beta to be f of y, x and y are fixed here. Okay, x and y are fixed. Then for any f, I get a gxy such that dxy at x equal to f of x and gxy at y equal to f of y. Okay, here this is alpha, this is beta in the statement. Then we can get this. Okay. Now I define the following. You fix x. Now fix x for the time being. Okay. I mean, for each x, it's going fix. X is arbitrary, but you fix it. In the discussion, I'm fixing. X is arbitrary. Okay. Fix x and define ux uy equal to all those z in x such that z in x such that g xy z is less than or equal to f of z plus epsilon. See, this is why we want to use this kind of thing. That is why it's important that it's real. It's real value. Okay. So this is one side we are approximating in this u alpha. And we know that y is in this side, right? G xy at y is equal to g of, I mean, equal to f of y, which is less than, which is equal to f of y. Okay? I mean, no, I take this. I mean, yeah, which is equal to y plus epsilon. There is an epsilon. This is equal to that. That's no problem. Okay. So note y is in uy. So union of uy equal to x, y in x is x, whole of x. So there exists y1 by compactness. Y1 up to yn such that union of I equal to 1 to n u yi, okay, is equal to x by compactness. Okay. So if you take the union over all uy, that's going to cover because each y is in uy. But there you only require finitely many of them because of compactness, thanks to compactness. So you have this. Okay. Now you look at the x, vary the x. Okay. Notice that. So let gx equal to minimum of gxy1, y1, gxy2 up to gxyn. Okay. Minimum of this up to a equal to 1 to n. Okay. Then gx at x for all of them equal to f of x, of course, because all of them satisfies that. Okay, this is true. And define bx equal to all those z in x such that f of z minus epsilon is less than minus epsilon is less than g x of z. Okay. Notice x is in vx. Okay. So again, using the same trick, union of vx should be all of x. So there exists vx1 up to vxm. Okay. Open. They are all open, of course. This is all open. This is open. We are using that. This is open. This is open. All that. We are using the continuity because of continuity. This is open. This is open. Okay, we are using that. I forgot to mention. So this is also open. So this is open, and x equal to union of i j equal to 1 to m bxj. Okay. So this is gx1, gx. There is gx1 up to gxm. Okay. Now define g to be. There I use a minimum. No, this should be maximum. Maximum of gx1 up to gxm. Notice that we have taken the minimum of that. So gx will satisfy, still gx will be less than this. So it will satisfy this condition. Here we have taken the maximum of that. So all this g will satisfy this. It will be greater than this. So we have g of z is less than or equal to f of z plus epsilon and f of z minus epsilon. That is f of z minus f of z is less than. This is what we want to prove. Okay. We use the fact it's separate point and the constants are there. We need that. So as I said, you for any 2 points you get it, then use the compactness, use the openness, compactness, and to argue this. So this proves the original Weierstrass theorem. We haven't used it. Okay, it's not a cyclic argument. We only use that square root t is can be approximated by polynomial. This proves if you take any intervals, corollary polynomials are dense in C of any interval AB. This is compact CAB. And polynomial separates points, you can easily prove. Okay, and constants are there. I mean, you should consider constant polynomial also. Okay. So, and also you can prove if K is contained in Rn, compact. and polynomials in n variable, x1 up to n variables, which is a function on Rn, right? Polynomials in n variable is a function on Rn. Okay. In C of k is dense. You can prove something more. Exercise. Okay. You have to prove that they're separate points. Given any 2 points, you can different point, they will differ at some coordinate. You can find a polynomial, which this is same as real line one. Okay. If you have 2 element here, they will differ at some point. Then you can find a polynomial which differ. So this is clear. And the next topic we are going to discuss is Fourier series. So in that I will be using this. I will be using a slightly different version on trigonometric polynomials or something. Now I have to think about notation. Let interval 0 to 2 pi. Let me take the interval 0 to 2 pi. T interval 0 to 2 pi. T1 means something. If I put Z0, usually C0 is used for locally continuous function or locally compact function, locally compact space, which vanishes at infinity or something. But this notation maybe I use a different notation. What should I want to consider this function f in C of 0 to pi, all continuous function, which coincides at the endpoints, such that f of 0 equal to f of 2. Okay. Not all continuous function, which are same at the endpoints. Okay. So what is the notation I? Okay, for the time being, I put a 0 here. The confusion is usually if you have a locally compact space, C0x is usually, locally compact space, there is something called function vanishing at infinity. Okay. Maybe I will do it in the next class. Okay. So it is used for that. Okay. For the time being, it is this. Maybe when I do Fourier series, I will change the notation. I'll think about it. Okay. So this is the handy notation. Okay. So this is this. Now I want to prove the following. I want to prove the complex valued one. Let me prove the complex values for Stone-Weistrass theorem and come back to this. Without that also one can prove, but it's easier to do that. So theorem, Stone-Weistrass complex value. Complex version. Okay. That A contained in C of X, C. Okay. Subalgebra. It's a sub-contained constant. Separates points. Further, and closed under adjoints, closed under the conjugation. Okay. This is one more condition. There is no conjugation in real line. Here closed under conjugation, which is also called as, I said it adjoint. That's because it's like adjoint. To consider as adjoint of a matrix, no? Like that, there's an adjoint for linear operator, and it will be actually an adjoint in some sense. Okay. So that is f in C of x. Then you can take the bar, which is a conjugation is a continuous function. F bar is also in, f in A, then f bar is also in A. Okay. Then A closure equal to C of x. Okay. C of x, C. So that A R equal to all those f in A, such that f of x is contained in R, or real valued function. Okay. I take all real valued function. Call it as AR. First, I want to prove that I'm given a like that. Then I define an AR. I want to prove that this AR is dense in all CXR. Okay. First claim is contained in CXR, which is of course contained in CXC, of course. The real valued means it's complex valued also, is dense. So how do we prove it? So if F is in, so I have to, so it contains constant, of course. This is a subalgebra. This is a real subalgebra. Okay. If it's real value, it's a real subalgebra. I mean, real vector space and it's subalgebra. Product is there, of course. Okay. Product is also real value, so it is there. I mean, from A, I have taken all the real value. If you take F and G are real value, F product is also real value. So it's a subalgebra. And it contains constant, real constant. So it contains constant in for the real case. And it separates points. Only thing I have to verify, it separates points. So if X is X and Y in X, then there exists a F in A by whatever the condition is given. F of X is not equal to F of Y. Okay. But then it should differ in either real part or imaginary part. Okay. Now that is either real of F at X is not equal to real of F at Y, or imaginary of F at X is not equal to, one of them should be true, right? Two complex numbers are not equal, either is true. But then both real of F and imaginary F, but real of F, imaginary of F, they are real value functions, right? Because you know the trick. Real of F equal to F plus F bar by, because F bar is in A, F is there, F bar, the condition we are using. F bar is there divided by 2, and imaginary F, you can multiply by constant, F plus F minus F bar. So because of that, so this is continuous, this is, I mean, this A is an algebra, and A is closed under bar, and there is a subspace. We are using that, so these are all in A. They are in A and they are real value. That's all. Okay. AR is just all real valued function. So it is there, and one of them should be not equal to that. So it separates. So this implies AR is dense. Separates points and it is dense by the earlier version. Okay. Oh no, it didn't change. Forgot it. Unfortunately, I forgot to change. Anyway, the proof is easy. And now it's clear, no? If F is in P of X, P, okay, then real part of F, real part of G, real part of, sorry, imaginary part of F are in CXR, of course. Of course, it is always compact. Started from that. Otherwise, it's not a, I mean, norm in F infinity you cannot define, no? Norm F infinity, supremum, it's only bounded functions. It exists for bounded functions. Otherwise, you have to consider bounded functions and all that. Okay? So these are real value functions. We have already proved AR is there. So there exists Fn, Gn in sequence contained in AR such that Fn converges to real of F, Gn converges to imaginary of f. Of course, you know that Fn plus Ign will converge to, you call it F1 or F2. F1 plus F. Here, because there is a F1 here. So here of F plus I times imaginary. That's all. So from the real version, we can prove the complex version. Okay. Now I consider this example. All function which coincides in the endpoints. Okay. Then the claim is then this kind of thing. Summation n equal to minus n to this kind of thing. What is called, you'll see, this will be some sort of Cn e power inx. Okay. The n in, well, Cn is in C and n in Z is dense. That whatever E0, 0, 2, 5. Okay. These kind of, which are called trigonometric polynomial or something. This is not trigonometric polynomial, but if you write it as cos nx, cos nx plus I sin nx, then the imaginary part, real part, they will. Yeah. So why is this true? I can't apply directly the Stone-Weistrass theorem for this because this is a different one. And all these functions coincide at 0, coincide at 0 and 2 pi, right? When x equal to 2 pi, it's going to be 1. 0 also, it's 1. Okay, cos is, okay. So they coincide at the endpoint. So they don't separate points, right? They have the same value at endpoint. They will take different, they don't coincide. So we can consider, we can identify this set. We'll come back to this again. C0 2 pi is 0 2 pi is same as C of the circle. Circle, how do you write? This is okay, this is circle. T or circle, almost. C of this set. Z in complex number mod Z equal to 1. Or you don't like it, I am just, my statement is span of Z power n in Z, okay, is dense in this. This is, I call it T or something. This is C of T. Circle in complex plane is compact. Okay, this set is a compact set. This is continuous functions on that. Now you have Z power n, the same as that, e power anx, right? Okay, this kind of, this is functions. E power ix, everything will, you define the function from here to t to e power it, which will give you an identification from 0 to pi to circle. And it coincides in the endpoint. That will give you a homeomorphism between this metric space and this metric space. Okay, we will deal with, I mean, we'll talk about it again when we discuss Fourier series. So this is dense here. This span of this means you take span like that. Okay, span of this, linear span of this, not infinite linear span. Finite linear span of this is dense here. Okay, that's the statement. That is clear. All you have to verify is Now it's clear. This is continuous function, not like that. Now it will separate points. It contains constant. If you take just n equal to 0, it contains constant. Okay. And what? That's all. And the e power, I mean, because of it ranges from -1 to n, if some f is there, f bar is there. Yes. So from Stone-Weistrass theorem, it follows that these kind of elements are dense there. This is actually used to prove that this forms an orthonormal basis for some infinite dimensional. Huh? Closed under conjugation. This set. Yeah. N is in Z. Z square is Z power -2 because it's in circle. Right? Z bar is Z inverse. 1 by Z. In circle. Okay. So, and you can prove many other theorem. I mean, I want to prove it for either locally compact, I don't have time for that. So, I think I'll stop with this.